that are complex numbers, can we build a function from that? So let's say f of x has zeros, x equals 2, and then let's do 3 plus I and 3 minus I. Okay, so I've got two complex numbers here that are roots, and I've made them so that they have both a real and an imaginary part. And then we're going to see if we can put all of this together into a function. So we're going to write f of x in standard form. So if you see that, write it in standard form, that means you're going to have to multiply it all out. So the steps in this process are going to be take the zeros, make them factors, take those factors, multiply them all together. Be careful with the imaginary pieces of it as you do that. Okay? That's where it can get a little tricky. All right, so f of x. Each of these I'm going to turn into a factor. What's the factor that goes with x equals 2? X minus 2. Okay. The factor that goes with 3 plus I. Nope, we're just talking the factor. So it would be x. It's always x minus whatever the root is, right? And that works for complex numbers as well. So it's x minus 3 plus I. Like that. And then the other one, x minus 3 minus I. Okay, so always kind of stick to that formula. X minus the root. X minus the root every time. Now, you can simplify these up a little bit. You got to distribute the negative each time. Before you start to multiply, I would definitely do that. So x minus 2, this is x minus 3 minus I, and this one would become x minus 3 plus I. And then we're just going to start multiplying everything to everything. Okay? Now, my suggestion to you before you start going after that, take care of the ones that have the imaginary numbers in them first. Because if you're doing your math correct, you should eliminate all of the i's from the equation by doing that. And I'll show you that process here next. After you have that done, then take that answer and multiply it by x minus 2. It should be a lot less work to do. Okay, so I'm going to leave this one alone. And let's just be very careful. Every part of this multiplies to every part of that. Okay, so x times x, x squared, x times negative 3, x times I, and then go to negative 3. So negative 3 times x, negative 3 times negative 3, negative 3 times I, negative I times x, negative I times negative 3, and negative I times I. Okay, so it's all of that. All right, there should be, like I said, a lot of cancellation happening if you've done all of your multiplying correct. So do you guys see any of it? What should be canceling in there? Pretty much everything with an I in it, except for the I squared. Yeah, but that will take care of a different way I'll show you. So, yeah, so there's this plus ix minus ix. Minus 3i plus 3i. All that's gone. So we got x squared minus 3x plus 9 minus I squared. Broken it down to that. So the 3x's can go together. So x squared minus 6x plus 9. Now, what about this I squared? Yeah. Right. Because remember, I is the square root of negative 1, right? So I squared should just be negative 1. Get rid of the square root symbol, right? So I can take that and turn it into a negative 1, but be careful because it's negative I squared. So it'd be a positive 1, right? So that plus 1. So what we really have here is x squared or x minus 2 times x squared minus 6x plus 10. So like I mentioned, if you've done your multiplication correctly, there shouldn't be any i's left. And now it's another just be careful, multiply, multiply, multiply type thing. So x times x squared is x to the third, x times negative 6x, x times 10, negative 2 times x squared, negative 2 times negative 6x, and negative 2 times 10. And do a little combining like terms. We'll get our final equation for f of x here. So x cubed minus 8x squared plus 22x minus 20. So apparently this polynomial has the roots 2, 3 plus I, and 3 minus I. That's what we did. We used the roots to go back the other way. Is this a little tedious? Yeah. A little bit with all that multiplying. Is it easy to make a mistake? Yeah. So you got to be careful of that too. More often than not, though, we're not going to go this direction. We're going to go the other direction with it. But I like doing these kind of problems as part of the notes, though, just because it helps you to see the connection between the zeros and the equation itself. Okay, whatever those zeros are, real or complex, you multiply them together as factors, and that gets you the equation for the polynomial from whence they came. So it's a good connection that way. So one thing that maybe you noticed about this one is those two complex roots that I gave you. What do you notice about those two? Are they similar in any way? Yeah. Right. They're alike, except one is 3 plus I and the other one's 3 minus I. There's a special name for that. It's called conjugates. Okay. If you have two terms that are exactly the same, except one's being added and one's being subtracted, those are called conjugates. So these are called complex conjugates. And what ends up happening with every one of these problems that end up having imaginary solutions or complex numbers that are in there with imaginary parts, they always come in these conjugate pairs. There's a plus and there's a minus. Even look at the one that we did before it. Take a look at the two answers that had imaginary parts on them. Aren't those conjugates technically? It's with 0, but it's still a conjugate. 0 plus the square root of 2i and 0 minus the square root of 2i. They came together again as a conjugate pair. Okay? And that's another theorem that we're going to look at here involving complex roots. You never have a complex root with an imaginary part by itself. It's always going to have its conjugate pair coming with it every time. Okay? So I'm going to jot that down. And we're going to use